हेलो फ्रेंड, वेलकम बैक टू अवर न्यू वीडियो। आज के वीडियो में हम चैप्टर नंबर 2 जिसमें हम स्टार्ट करेंगे रिलेटिविटी सेकंड, और टॉपिक का नाम है रिलेटिविस्टिक मोमेंटम। In this opening section, chapter 1, we discuss the classical observation that if Newton's second law F equal to m hold in a particular reference frame, it also holds in any other reference frame that moves with the constant velocity relative to it. For example, in any inertial frame, it shows the section what the Galilean transitions to the structured springs are also same in the both frames. However, according to the Lorentz transformation, acceleration are not same in two such reference frame. If a particle has acceleration Ex and velocity Ux in the frame's acceleration is not obtained by the computing equation A naught x equal to Ax over lambda cube 1 minus Ux over x c square whole cube. This F over m must transform in a similar way, or else Newton's second law F equal to ma does not hold. It is reasonable to expect that F equal to ma does not hold at high speeds, for the equations implies that a constant force will accelerate a particle to a limited velocity if it acts for a long time. However, if a particular velocity were greater than c in some reference frame S, so we could not transfer from S to the rest frame of the particle because lambda imagines when we greater than c. We can show from the velocity transformation that if a particle velocity is less than c in some frame S, it is less than c in all frames moving relative to S with having less than c. This result leads us to expect that particles never have speed greater than c. Thus, we expect that Newton's second law F equal to m. In law of relativity in minute, we will therefore need a few law of motion, but one that resembles Newton's classical version when beta equal to v over c. In this chapter, we will also explore the change in the classical dynamics that are dedicated by the relative theory, directing particular attention to the same concept around which classical mechanisms are developed. Namely mass, momentum, and energy. We will find these changes to the very beta dramatic are those who we encounter in chapter 1, including a Lorentz transformation for momentum and energy and a new irrelevant quantity to stand beside the invariant spectrum intervals del S. Then in the later part of the chapter, we will briefly turn our attention on non-minerals or accelerated reference frames. They relate the theory of the general relativity. Relativistics of Momentum are among the most powerful foundational concepts that you have thus studied in physics until they are ideas of conservation of momentum and conservation of total energy, as we will discuss a bit further in chapter 12. Each of these fundamental laws areas because of the particular symmetry that exists in the laws of physics. For example, Indeed, Einstein first postulates that used Lorentz transformations guarantee this later relevance. All inertial frames, the simplicity and universality of these conservation laws leads us to seek equations from relative mechanics. Replacing equations, they are consistent with the momentums and energy conservation and are also invariant under Lorentz transformation. However, it is straightforward to show that the momentum as formulated in classical mechanics does not result in a relative invariance of the law of conservation of momentum. To see that this is so, we will look at the isolated collision between two masses where they are avoid the questions of how to transfer force because of let external force is zero in a classical mechanics. If the momentum is to be conserved, the y couplet must be zero because momentums of each ball is linearly reversed by the collision. However, if we consider the relativistic velocity transformation, we can see the quantity m uy does not have the same magnitude for each ball as seen by other. In this frame, balls are moving along the y-axis with velocity u y equal to u naught. Ball B has x components of velocity u और b equal to v as y component. Equation देख लीजिएगा. So next here we have used the velocity transformation equation 122 and the fact u naught is just u naught is u naught x b equal to 0. We see that the y component of the velocity of ball B is the smaller in magnitude than the ball. X is greater than the time measured by a slot for the ball is traveled to the same distance. Thus, less today y couplet of classical momentum is not zero since y couplets of the velocity momentum is defined by p equal to sigma mu is not conserved in S analysis of this problem will S leads to the same conclusion. Momentum is conserved of the course because of the fact lambda equal to approximately u. The result of the for defining momentum as sigma mu is classical mechanics is that a quantity is conserved when there is no external force. In our collision examples, we know that this quantity is conserved only in the approximate y. Let's see. We will define the relative momentum p of a particles to have the following properties. First, p is conserved in the collision. P approaches mu as u or c approaches 0. Let's apply phi of this collision to the collision of two balls that we just discussed. Let's think two important points. First, we will find the observer. The speed of each ball is unchanged. The speed of each ball is unchanged by the classical collision if either u naught. Second, the failure of the conservation of momentum. The collision we described cannot due to the velocities because we used the Lorentz transformation to find the y components. It must have something to do with the mass. Let us write down the conservation of y component to the momentums are y observed as keeping a masses of two balls straight by writing for the s observation on ball. If a ball is compared to the relative speed v of the reference frames in order the following equations, if we can now imagine to the limiting where you lot where each of the ball is rested hoop frame the collision becomes aggressive as one B moves past at a speed v equal to u, so we conclude the equation m u equal to v over m u lot equal to z o u lot over u lot 1 minus v square over c square whole का cube m into u m over 1 minus v square over c square whole का cube. Suppose says that observer is measure the mass of the ball moving the relative to him speed if equations times the rest mass of the ball or its mass measure the frame in which it rests. Notice the observer always survive the mass of frame which is observed in the expected of them larger than the value measured when he objecting at rest. Thus we see the law of conservation of momentum will be said in the relation it provided that we write the momentums p of an object with the rest of the mass m p equal to m u over 1 minus u square over c whole cube, where u is the speed of the particles within the take equation and the definition of relative momentum. It is clear that the definition means our cycle. This use of the symbol lambda for two different equations causes some confusion. The notation is tailored. However, the simplified value of the equation we will use this equation expect will be also citing transformations between reference frames. We will avoid using the term of the symbol for relative mass in this book. I will always refer to the mass. So thanks for watching our video and don't forget to subscribe our चैनल फॉर मोर अपकमिंग इंफॉर्मेटिव वीडियोस। तब तक अपना ख्याल रखिएगा, मिलते हैं लाइव वीडियो में। अल्लाह हाफ़िज़।